Hello everyone, my name is Naoki Shiraishi with National Agriculture and Food Research Organization called NARO. So today I'm going to talk about ionic liquid gated graphene FET sensors for detecting NO3-N in agricultural soil. I will divide my talk into 5 parts: background, goal, principle of sensing, and development of ionic liquid gated graphene FET sensors, evaluation, and conclusions. So our vision is to build a data-driven smart agriculture system based on crop growth status and environmental information in agriculture soil. So we will develop the systems related to sensing, planning by AI, and actuation by smart agriculture robots. So NO3-N is one of the most required sensing targets because the NO3 absorption affected by the growth of the plant, especially leaf. Now we measure the NO3-N concentration in the laboratory. So before measurement, the sampling of soil solution is needed. We set filter into agricultural soil and apply negative pressure to change to obtain the soil solution. So it's not good for local monitoring. So if we measure the NO3-N concentration, from the vapors of soil solution containing NO3-N, local time monitoring is realized. So my goal is development of NO3-N sensors for local monitoring in agriculture soil. So I think ionic liquid gated FET sensor have good potential for this purpose because low power consumption and small and high sensitivity. Okay, let me move on to principle of the sensing. Okay. This shows the schematic of the sensor and how the ionic liquid gated graphene FET sensor detects NO3-N. The sensor consists of graphene channel, electrodes for gate, drain, and source. The ionic liquid covering the channel, graphene channel. So if the gate voltage applied ionic liquid, the electric double layer of non-conductive is formed. Then the sensor exposed vapors of soil solution containing NO3-N. The NO3-N absorbed on surface on the ionic liquid, and NO3-N diffused into the ionic liquid and doped into the graphene channel as a charges. So the transfer characteristics curves was shifted. So hence the concentration of NO3-N can be detected by the shift of the transfer characteristic curves. Okay, then we will move on to development of the sensors. This shows the fabrication process of ionic liquid gated graphene FET sensors. First of all, graphene channel forming. Next, electrodes patterning. And then cytoforming and graphene channel release. These pictures show the photograph of the processed graphene wafer and enlarged same image of graphene FET sensor. The sensor composed 6 channels, have different channel dimensions. And finally, ionic liquid forming. The ionic liquid of PMMM BF4 is used in this research. This picture shows the enlarged micrograph of channel 6 and external view of the sensor set onto the package. Okay, this shows the basic characteristics of sensors. The left figure shows the relationship between drain source voltage and drain source current. The higher, a wider and shorter channel tend to exhibit higher conductance. It means high sensitivity. The right figure shows transfer characteristic curves in vent air at room temperature. The transfer characteristic curves were typical of graphene FET. So increased both negative and positive side from Dirac point. Okay. Let me move on to evaluation of detecting NO3-N. So we developed the soil simulated system. Our system consists vaporizer, temperature chamber, and sensing circuit. The vaporizer composed heater and pellet device. The heater vaporized soil solution, and pellet device offset the temperature change caused heater. So our system creates and supplies the vapors of soil solution in the chamber. This shows the external view of the sensing circuit. The Ionic liquid gated FET sensor installed in the sensing circuit. And our sensing circuit has temperature and humidity sensor. Okay. Before evaluating the NO3 sensing, we measure the ultra pure water response of the sensors. So ultra pure water of 10 milliliters applied to vaporizer and measure the transfer characteristic curves, and time interval is 5 minutes. So humidity in the chamber shifted upwards for 20 minutes, and Dirac voltage increased with humidity for 20 minutes. And after 20 minutes, humidity is stable. And Dirac voltage also stabilized at 0.7. And curves converges in 60 minutes. And next, we evaluate the NO3-N response. 1000 ppm of NO3-N applied to vaporizer and measure the transfer characteristic curves. So humidity in the chamber shifted upwards for 20 minutes, and Dirac voltage also increased with humidity for 20 minutes. And after 20 minutes, humidity is stable, but the Dirac voltage of the sensor decreased from 0.7 to 0.5. So this seems to be affected by NO3-N absorption. The curves converges in 100 minutes. And finally, we measure the concentration dependence of the sensors. 100 ppm and 1000 ppm NO3-N of 0.2 milliliter applied to vaporizer in chamber and vaporized completely. The humidity in the chamber increased from 30 to 40% and stabilized. The transfer characteristic curves of 100 ppm and 1000 ppm were measured 40 minutes after exposure, respectively. So this lower figure shows the NO3-N response of the sensors. The blue line is 100 ppm. The red line is 1000 ppm. So the Dirac voltage changes 0.1 volt to negative side as the NO3-N concentration increased. So this means the ionic liquid gated FET sensor can detect different NO3-N concentrations in vapor depending on the shift in the transfer characteristic curves. Conclusions. We fabricated ionic liquid gated graphene FET sensors. We developed the soil simulated system equipped with a vaporizer, chamber, and sensing circuit. The Dirac point voltage changes to negative side as NO3-N. The ionic liquid graphene FET sensor can detect different NO3-N concentration in vapor depending on the shift in transfer characteristic curves. Thank you.